All right, so it's a great pleasure to introduce all the way from New York City, Chris Conidis, who's going to talk to you about reverse math of NIMIT of some decomposition lemma. Chris, go for it.
All right, thanks, Peter, and thanks everybody for having me. It's been a while since I've spoken at the Midwest Computability Seminar, so it's always nice to be back. And, yeah. So just thinking about the last time I spoke here, like I understand a lot more about things now. So it's nice to you kind of revisit the old talks, and you realize the progress that you've made. So it's nice to come back. Okay, so today I want to talk about the reverse math of Noether's decomposition lemma. This is this decomposition lemma is sort of it's a standard theorem that you see in any sort of introductory commutative algebra course. And I want to look at the reverse math of this thing, because it turns out to be a little bit more interesting than some of the other standard algebraic theorems. All right, so just some definitions. We get some definitions out of the way here. So by a computable ring, all I mean is a computable subset of natural numbers equipped with two computable binary operations. So addition and multiplication on a computable ring. Addition is computable, multiplication is computable. And I'm going to assume that my rings are all commutative here, and they all have a 0 and 1 element. They all have the structure of a ring. All of my rings are going to be countable, right? All of my rings are going to be countable. Okay, so now for the primary decomposition lemma. So what Noether's primary decomposition lemma says, so this is not standard terminology, I should start with that. So I'm calling this thing a primary decomposition lemma. What is more standard is the primary decomposition theorem. That is the standard terminology, but I'm calling this the primary decomposition lemma because, especially from a reverse math point of view, at least the way it's looking to me right now, this is sort of the key. This is the key lemma, and I sort of on my way to proving that it's the strength of the primary decomposition theorem is the same as the strength of this lemma, and so this is the key lemma in terms of the reverse mathematical strength. We'll say in terms of somewhat in terms of the combinatorics. Let's say. So this lemma, you can find this lemma in every introductory commutative algebra textbook. It won't necessarily be labeled as such, but you can find this statement. And the statement says that if you have a Noetherian ring, then it only contains finitely many minimal prime ideals. And so something to keep in mind with minimal prime ideals is that the zero ideal is potentially a minimal prime ideal. And so if you're in an integral domain, 0 is going to be the unique minimal prime ideal. And so if you have more than one of these things, you are necessarily not in an integral domain. And so a lot of the rings that we're going to be working with today, in fact, all the rings are not going to be integral domains. It's something to keep in mind.
Question?
Yeah.
Could you remind me what a Noetherian ring is? Does this have to do with descending chain condition or something?
Yes. So a ring is Noetherian if it satisfies the ascending chain condition on its ideals. And so you can't have an infinite, strictly ascending chain of ideals in a Noetherian ring. And in terms of reverse math, we usually, the way to sort of look at these things in terms of reverse math, you want to look at things in terms of set existence theorems. And so the way that you analyze something like the primary decomposition lemma in terms of the reverse math is that, in general, the way that you would analyze a theorem about Noetherian rings in the context of reverse mathematics, typically a natural way to sort of do it is to look at the theorem that says, if you satisfy all of the hypotheses, but you don't satisfy the conclusion, if you satisfy all of the hypotheses except potentially the Noetherian hypothesis, but you don't satisfy the conclusion, then your ring is not going to be Noetherian, and so you have the existence of this strictly ascending chain in your ring. And so that's the way that I want to look at the theorem here. And so the primary decomposition lemma for me in the context of reverse mathematics, it says that if R contains infinitely many minimal prime ideals, then R is not a Noetherian ring. And if you're not Noetherian, then you have a strictly ascending chain of ideals in your ring. And so when I mention the primary decomposition lemma, this is the way that I'm going to think about it. And it turns out that even if you think about it this way, there is a fairly straightforward proof of this thing. Classical proof. There is a fairly straightforward classical proof of the primary decomposition lemma. And so to prove this thing, it's not that hard. You basically assume that you have a ring that contains infinitely many distinct minimal primes. And the goal is to construct an infinite strictly ascending chain of this thing. And the way you do that is you just start with the zero ideal, fairly easy. Now, since R contains infinitely many minimal primes, remember that zero counts as potentially a minimal prime, but because we have infinitely many of these things, zero is not prime. And because zero is not prime, you can find two elements, A1 and B1, such that A1 and B1 multiply to be zero, which is in the initial ideal, I0, which is just the zero ideal at this point. And so because you have a product, A times B is equal to zero, either A1 or B1 has to be contained in each one of these minimal prime ideals. And so we have infinitely many distinct minimal primes. And so for one of these two elements, either A1 or B1, one of those two things has to be contained in infinitely many minimal primes. And so you choose the ring element, either A1 or B1, you just choose the one that belongs to infinitely many minimal prime ideals, and then you add it to the initial ideal I0 to get I1. And so this is sort of an algorithm, an algorithm relative to zero double that decides whether or not you put A1 or B1 into the ideal I1. And then if you just repeat this thing, you can repeat it uniformly using a zero double prime oracle, say. You can repeat this argument over and over and over again to construct a strictly ascending chain of ideals in your ring, right? And so the kth ideal in the chain is going to have k many generators. Using this zero double prime oracle, you can do all this. And so this is a classical proof of the primary decomposition lemma. So it's a fairly straightforward argument that uses zero double oracle. All right. So now that we've talked a little bit about the primary decomposition lemma, I want to get into the reverse math of this thing. So I'm going to start off by just reminding us that in reverse math, we sort of have these big 5 subsystems of second order arithmetic. In the context of algebra, the 3 most important ones in the context of algebra is ACA naught, WKL naught, and RCA naught, right? And so RCA naught, that's just recursive comprehension. And WKL naught is weak Koenig's lemma. It says that every infinite binary branching tree has an infinite path through it. And then we have arithmetic comprehension for arithmetic predicates. Okay, so typically theorems from algebra, they tend to fall into either RCA naught or WKL naught or ACA naught. There are some that are known to be equivalent to Pi11 comprehension. I'm not sure about ATR. There are probably 1 or 2 that's known to be equivalent to arithmetic transfinite recursion. But for us, especially in the context of commutative algebra, and well, we'll just say that, so I'm typically working in, a lot of my research is like, it's like the first 50 to 100 pages of a commutative algebra textbook. And those tend to fall into either RCA or WKL or ACA. If you're in the first 50 to 100 pages of a commutative algebra textbook, you're probably one of these three. In the context of this talk, though, there's going to be some other ones that sort of come into it. So some other subsystems of second order arithmetic. One of them is the ascending descending chain principle, right? So this says that every infinite linear order has either an infinite ascending chain or an infinite descending chain. The existence of two random sets, and so every set has a set that's two random relative to it. That's also going to be relevant, as well as the cohesive set principle and the atomic model theorem. These are subsystems of second order arithmetic that are going to be relevant for the primary decomposition lemma. Although I'm not going to get too much into the specifics of these sorts of things, because I want to get into the algebra a little bit more. But these are axiom systems sort of keep in mind when talking about the primary decomposition lemma. All right, and so with those in mind, I want to introduce a combinatorial principle that I call the tree anti-chain theorem. And so before I do that, I want to introduce a class of trees. I'm going to say that a binary tree T is completely branching if for all nodes in the tree, either both children of the node are in the tree, or else neither child of the node is in the tree. So either you split and both children are in, or else you're a dead end. And the tree anti-chain theorem says that every infinite completely branching computably enumerable tree contains an infinite anti-chain. All right. And so this is a slightly awkward phrasing because I'm talking about these computably enumerable trees, and I could be doing this over RCA naught. There's an equivalent version of the tree anti-chain theorem that says every infinite tree with no terminal nodes and infinitely many splittings has an infinite anti-chain. All right, it doesn't matter over RCA naught, doesn't matter which one you take, they're both equivalent over RCA naught. Although I will mention that they may not be uniformly equivalent. If you up the uniformity condition on the reductions, I'm not sure. There is a non-uniformity. There's some non-uniformity in the proof that these two are equivalent.
Hey, Chris.
Yeah.
Are these binary branching or?
Binary branching, yeah. Yeah.
Okay.
Yeah. Yeah. And so basically, if your tree sort of has infinitely many splittings, then it has an infinite anti-chain. Yeah. That's all I'm really saying here. I tend to work with the first version. It's a little bit more natural. It's more natural to me. It's more natural to me to work with the first one with these computably enumerable trees. And
in the first of these two versions, you have computability as a requirement, and it's not in the second one. Is it needed there also?
Yes, it is needed. So the first version is computably enumerable, and the second version is just computable. So yeah, so I've left out the word computable. It's a little bit ambiguous the way that I've phrased.
What is the role of computability in this approach anyhow?
Yeah, it's not really that important. It's not really that important. It's only so I'm making this definition over RCA naught. That's all I'm really trying to say with this, with the computability considerations.
Chris, can I ask a quick question?
Yeah.
So am I understanding correctly that in the second version, the infinite tree is just in the second order part of the model, and in the first one, it's sigma 1 definable over the second order part?
Yes.
That's what technically what it is. Oh, okay.
Yeah.
Just making sure. Thank you.
Yeah. And so the second version has no terminal nodes, right? It has no terminal nodes. And that's sort of how you pad out your enumeration of these splittings, because the first version talks about, completely branching computably enumerable tree. And remember, when I say completely branching, I mean everything, you're either split or else you're a dead end, right? And so you basically pad out this completely, these branchings from the first version to the second version with the no terminal node condition. So you just keep extending everything, and then every once in a while you're going to split in the second version here. And so this computably enumerable thing just basically becomes no terminal nodes. You pad the thing out with sort of these isolated paths as you go up. All right, so this is the tree anti-chain theorem, and it's related to Noether's primary decomposition theorem. Okay, so some little bit of reverse mathematics. I don't want to dwell on this too much. There's more to say here, but I do want to just mention a little bit about the reverse math of this tree anti-chain thing, because it is interesting. So first of all, it follows from the existence of two random reals and the ascending descending chain principle individually. So there's a proof from 2MLR and there's a proof from ADS, two different proofs. And it falls into a syntactic class of statements that are called restricted pi12. All right, and this is, you can find these things in the paper by Dennis and Richard, and also Dennis, Richard, and Ted's paper. So the first paper is about its combinatorial principles weaker than Ramsey's theorem for pairs, and the second paper is about the atomic model theorem. But they define a class of statements called restricted pi12, and there's certain conservativity properties for these sorts of principles. And so from these two facts, you can show that this tree anti-chain property, it's not equivalent to any other what I'm going to call known subsystem of second order arithmetic. I mentioned this in my talks usually now, but if you go to like Demir's website, he has this big PDF there, this tree anti-chain principle, it's not equivalent to any other thing in what Demir and other people are calling the zoo.
Question: there must be something else involved here. If you take a statement that's provable in RCA naught, it obeys both of these facts, but doesn't obey the corollary. So how do you know that TAC is not provable in RCA naught, for example?
So it doesn't follow from weak Königs lemma. Yeah, so that is a good point. I probably should have put that in there. Yeah. So you need that too. So it's not provable from weak Königs lemma. I should add that. And that is a separate proof. Yeah. I should probably add that to the slide. So with all these things in mind, basically, the way that you prove that this thing's not equivalent to anything else is you need to avoid upper cones and you need to avoid lower cones. And the way that you avoid upper cones is to use the measure 1. So the fact that this thing follows from 2MLR, you use that thing to typically avoid upper cones. and then you use conservativity to sort of avoid lower commons. That's just it's a heuristic of how these things sort of go, but it's just a heuristic of how the proofs typically go for this tree anti-chain thing. Okay. So now I want to, one of the things I want to do next is I want to capture this tree anti-chain property using some algebra. So I want to sort of construct an algebraic principle that's going to be equivalent to this tree anti-chain theorem. And the way I'm going to do that is I'm going to use Noether's primary decomposition lemma in a relative to a restricted class of rings, basically. And so now I want to introduce a little bit of algebraic terminology. So we say that two ideals are coprime whenever their sum is the whole ring, right? And this means that you can find an element of one and an element of the other ideal that's sum to the identity element. So that's what it means for two ideals to be coprime. I want to say that two ideals are uniformly coprime if for all x in their intersection, there exists a y in the first one and an element z in the second one, such that, first of all, the elements y and z multiply to the original element x that was in the intersection, right? And so x can be sort of split as a product y times z in this way. And also at the same time, this is where sort of the uniform thing comes from, at the same time, there's a linear combination of y and z that is the identity. And so, so y and z both multiply to give you the x in the intersection, and you can generate the identity element of the ring from the same y and z as you did when you split x, as you got when you split x in this way. And this is just some terminology. So the first bullet point here is a standard algebraic definition. The second bullet point is, we'll say, less standard. It's sort of my own concoction. And they're both relevant in terms of this tree anti-chain theorem. So now, using these two definitions, I want to sort of, so as I said before, I want to capture this tree anti-chain property in terms of algebra. I want to sort of create algebraic versions of the tree anti-chain property using, using Noether's primary decomposition. And so I'm going to do this in sort of two different ways. So theorem A, one of the ways I'm going to do this is I'm going to say if R has infinitely many coprime minimal primes, then R is not Noetherian. All right. And so theorem A, it is the same as the primary decomposition lemma, except now I'm also requiring my infinitely many minimal primes to be, to be coprime relative to each other. So every pair of minimal primes, sums to the entire ring. And theorem B says that if R has infinitely many uniformly coprime minimal prime ideals, then R is not Noetherian. And so in theorem B, I'm restricting class of rings even further to these uniformly coprime minimal primes. And so I am requiring that my ring here has uniformly coprime minimal primes, infinitely many of them. And so here's a theorem A and here's a theorem B. And so it turns out that A and B are both equivalent to the tree anti-chain theorem, modulo maybe a little bit of induction. Theorem B is equivalent to the tree anti-chain theorem, and I called the second one a conjecture. It's getting closer and closer to being it's basically a theorem at this point. Officially, it's maybe still a conjecture, but I've been thinking about it more and more over the last month or two. and I haven't found anything wrong with the proof. So theorem B is equivalent to the tree anti-chain theorem, and theorem A is also equivalent to the tree anti-chain theorem over B sigma 2. So over RCA naught plus bounding for sigma 2 predicates. All right, so let's go a little bit into the proof maybe of this thing. I just want to sketch the proofs. The proofs are actually they're not that hard actually. So first I want to prove that, so here I'm just going to talk about theorem B. I'm just going to talk about theorem B, and remember that theorem B talked about these uniformly coprime minimal prime ideals. And so I have a stronger condition here in theorem B. I have uniformly coprime minimal primes. And so here, if I want to show that the tree anti-chain principle implies theorem B, I start with a ring that has infinitely many minimal prime ideals that are relatively coprime to each other, that are, sorry, uniformly coprime. And then given this ring, I build a tree such that every node in my tree corresponds to some, it's going to turn out to be a zero divisor. So as I mentioned earlier, these rings that we're going to be dealing with, they have a lot of, they are not integral domains, and they actually have a lot of zero divisors, especially if you sort of concentrate on the minimal primes, which is the only thing that you really know exists in them. So every node in the tree sort of uniformly corresponds to some zero divisor in the ring. And we also end up getting this condition here, that whenever you take a set S that sort of covers all of Cantor space, let's say a finite anti-chain that covers all of Cantor space, and you multiply the corresponding ring elements together. So if you sort of have a covering of Cantor space, that covering corresponds to, say, a finite set of ring elements. If you multiply those ring elements together, you're going to end up getting 0. You're going to end up getting 0, right? And what that means is that if you think about it, because you have a finite set of elements here that multiplies to 0, this means that every prime ideal is going to have to contain one of these x's that corresponds to an element of your covering. So basically every prime ideal, if you sort of think about it a little bit, but every prime ideal is going to correspond to basically a path through your tree. And so the way that it sort of works is that, you know, it's, so in terms of the minimal prime ideals, it's actually, so earlier here, I said in the definition of uniformly coprime, right? I said that this element X sort of splits into Y and Z. And the way it works in terms of the tree is that Y and Z are going to be children of X in terms of the tree, in terms of, you know, the correspondence between ring elements here and the nodes of your tree. And so because we have that uniformly coprime hypothesis, we end up getting that condition as well. And then basically what ends up happening is that, and here, you know, I'm not giving all of the details, but paths in this tree end up corresponding to annihilator ideals. That's basically what ends up happening. And maximal paths in this tree correspond to maximal annihilator ideals. And it turns out that maximal annihilator ideals in a ring are actually minimal prime ideals. Maximal annihilators correspond to minimal primes. And you can find this most recent bullet point, you can find this theorem in basically every commutative algebra textbook. And so the minimal primes are basically maximal paths through through your tree, and you have infinitely many of these minimal primes, and so you end up having infinitely many paths, and you end up getting infinitely many splittings, and you can apply the tree anti-chain property. Once you know you have infinitely many splittings, you can apply this tree anti-chain property to the ring, to the tree, sorry, and you can get an infinite anti-chain. And then using the infinite anti-chain in your tree, remember that every node in the tree corresponds to a ring element. You can take annihilators of larger and larger subsets of your anti-chain, essentially. So you take products of you end up taking products of ring elements that correspond to this anti-chain, and the more and more elements that you include in your product, turns out that the bigger and bigger the annihilator of that large product gets. And so you can create a uniformly computable, it's relatively computable from your anti-chain here, but going from this anti-chain to this infinitely strictly ascending chain of ideals, this construction is totally computable because of these annihilator ideals here, because you can take every element of your strictly ascending chain to be an annihilator of a single ring element. And so annihilator ideals are useful in this construction, and there's lots of them. There's lots of them around because we have these infinitely many minimal prime ideals, right? And so I've talked about this in some of my other research as well. Annihilator ideals, they lead to sort of interesting computability theoretic results. And one question I sort of like to ask after I'm done a project is like, how would I have known ahead of time that like it's Noether's primary decomposition theorem or primary decomposition lemma? Why would that have any interesting computability theory associated to it, as opposed to something else that's contained in another theorem, like let's say the Hilbert basis theorem, that's contained the first 50 to 100 pages of a commutative algebra textbook. And one context I will say that it can lead to interesting computability theory is when you have a ring that has a lot of annihilator ideals in it. All right, so this is the proof that the tree anti-chain theorem implies theorem B. For the converse, the way that you do it is you start with a sigma 01 is an infinite sigma 01 completely branching tree T, and then you want to somehow get an anti-chain in there. And the way that you do it is you build a ring. So you start with sort of this universal ring, and you use and so for the indices of your indeterminants here, you use the nodes in your tree to sort of index the indeterminants. You set the ring indeterminate corresponding to the root node of your tree. So the root of the tree is equal to 0. And then you use, so the fact that your ring is completely branching, either a node is going to be terminal or else it's going to split, it's going to have both of its children in there. And you use that splitting to define the multiplication relation here. And so the product of sort of the children indeterminants is going to be, is going to be sigma's indeterminate here. And notice that these first two bullet points, one of the corollaries of these, I won't go, I won't give the proof. I won't give the full proof, but you might find it believable that one corollary of these first two bullet points is that if you have, say, a finite covering of your tree, and because our trees are completely branching. A finite covering of my tree is the same thing as a finite covering of all of Cantor space. But if you have a finite covering of the entire tree, the ring elements associated to that finite covering are going to multiply to 0 for any finite covering. That just follows from these first 2 bullet points here. And so this ring, it's a little bit similar to the ring that we're talking about in the previous proof. And the last thing you do, once you impose the first 2 conditions, the last thing you need to do is you need to create inverses for all the polynomials. So this is a polynomial ring here that we start with, right? It's just a polynomial ring where the indeterminants are indexed by the tree elements over the rational numbers. And what you want to do is you want to include inverses for all polynomials such that the intersection of the partial coverings, and so if you have a polynomial, it's a sum of monomials, right? And every monomial you associate with a covering of Cantor space. Now every monomial, it can't cover all of Cantor space, or else it would just be 0 and you could just throw it away. Every monomial is going to correspond to a partial covering of Cantor space. And what you want to do is you want to invert all the polynomials such that the intersection of all the coverings of its individual monomials is empty. And so what that basically means is that for any element of Cantor space, you can find a monomial summand of your polynomial that doesn't cover that element of a Cantor space. And so basically you take this sort of localization here. This is a localization where you're inverting certain ring elements. And what that does is, taking this sort of localization, what it does is it leads to a principal ideal ring. It leads to a principal ideal ring where every ideal is just generated by a single monomial. Every ideal is just generated by a single monomial of the ring here. So this construction it's not a hard construction, but it leads to a very nice ring. It leads to a principal ideal ring where every ideal is generated by just a single monomial. And if you have an infinite strictly ascending chain, right? If you have an infinite strictly ascending chain, well, that's a chain of ideals. It's a principal ideal ring. And so every ideal has a generator. You can actually find that generator effectively. It's not that hard. Basically, because every ideal is generated by a monomial, right? You can basically, so the other thing maybe I should say here is that it's not just that every ideal is generated by a monomial, that is true, but every ring element, everything in this ring is a unit times a monomial. Everything in the ring is just that. And because of that, you can basically take an element of your ideal. That element is going to be a unit times a monomial, because everything in the ring is just the unit times a monomial. And then you can look at the exponents of your monomial. And then you can start asking whether you can decrease any of those exponents and still stay in the ideal. And so you can uniformly effectively find generators of any ideal in this principal ideal ring. And then you need B sigma 2 somewhere along the way, but using the exponents. And so the reason why I sort of went into that a little bit more details, because I wanted to sort of emphasize that the exponents come into it, but you use the exponents of these monomials, and using these exponents that you get in your infinite chain here, you can actually construct an infinite anti-chain of the tree T here by sort of paying attention to the exponents you see, and then looking at the corresponding index, because remember the indices of the indeterminants correspond to nodes in the tree. And so if you have a monomial, that's just a product of indeterminants. It's a product of tree elements, basically. If you pay attention to the exponents, basically watch where the exponents decrease, you can construct an anti-chain of your tree that way. And so these proofs are not really that hard. They're not really that hard. They use some basic algebraic constructions. One interesting thing that sort of falls out of this, and let me know how I'm doing on time. We're at that point where I'm not 100% sure, but just let me know.
You got about 15, 18 minutes.
All right.
Like that.
Thanks. So I want to talk a little bit about first order considerations. I gave this talk a couple of weeks ago at SEALS, and Jeff Hurst asked a sort of interesting question about first order considerations. And the truth is, I don't have a lot of substantial things to say, but I do have something that's kind of interesting to say about first order considerations of this tree anti-chain theorem. So over RCA naught, so not assuming any more induction than sigma 1, right? We know that the tree anti-chain theorem implies theorem B, all right? That, you just get it right out of the proof. You don't need any more induction to show that the tree anti-chain theorem implies theorem B. However, the converse, which is on the previous slide, I mentioned B sigma 2 here. I didn't go into it exactly how it's used, but you basically need to find an exponent sort of appears infinitely often. You need the infinite pigeonhole principle. You need an exponent that appears infinitely often, and then that gives you your anti-chain. So the converse requires B sigma 2. And so if you look at the proof of that converse, the proof it leads naturally to a class of sort of anti-chain principles in some way. It's a way of sort of weakening the tree anti-chain theorem into what is potentially sort of infinitely many different combinatorial principles. I say potentially because like I said, I don't have a lot of content here. I'm just sort of talking about interesting things. So maybe somebody knows more than me in the audience, definitely at this point. That could be. So I want to make some definitions here. And these definitions, the thing I sort of want to emphasize, I'll just say it now, is that all of these definitions, they fall right out of the algebra. Like, that's kind of the interesting thing about this, at least from my point of view. They all fall very naturally right out of the algebra. You don't need to think too hard about formulating any of these things in the context of algebra and Noether's primary decomposition and everything. So for each natural number n, let n-TAC be the principle that says for every infinite tree, infinite binary branching tree with infinitely many splittings, there is a path non-increasing function t to n. And so when I say path non-increasing, what I mean, maybe I'm being a little bit too clever here, but it's a non-increasing function from the tree to the natural numbers. Now, the tree and the natural numbers, these are, the tree is a partial order and the natural numbers is sort of a total order. But I want my function to be non-increasing. And so what that means is as you move along the paths of t, you sort of move up or down depending on how you want to draw your trees. As you move along the paths, your function is non-increasing along each path. Right? So just keep in mind that there are two different orderings here, right? One on the tree and then one on the natural numbers. And I tried to say it a little succinctly here just to sort of save space on the slide as much as possible. And so we have a function from the tree to the natural numbers such that the root node gets the value n. And so this n that I'm talking about in the first bullet point, that is the same n that appears at the very beginning of the definition, right? And so the definition begins for each natural number n. That same n, that gets the root of the tree gets that value n. And then the other thing I'm going to require of this function, in order to make this function interesting at all, basically, I need infinitely many nodes at which the function decreases when you move from a node to its successor node, to either one of its children, either one or the other, maybe both. And so here, I am asserting the existence of this function f. And it turns out, maybe you can do the proof in your head, it's really not that hard. It turns out that the tree anti-chain theorem is just equivalent to one TAC in this sort of parametrized tree anti-chain theorems. So the regular tree anti-chain theorem, the one that I've been talking about, that's just one TAC, where you assign the root node a value of 1, and then your function has to decrease infinitely often from that point. And so the places where your function decreases, that has to be an anti-chain. That just has to be an anti-chain. And so now the last thing I want to do in this definition, now that I've done it relative to this parameter n, I want to say let WTAC, or the weak tree anti-chain theorem, the weak tree anti-chain principle, be the n tree anti-chain principle without the n. And so basically you just remove the first bullet point here. And so there exists an n that you assign the root to, but you don't specify what value the root gets. And so I'm going to call that the weak tree anti-chain theorem. And so there is just some function where the root gets some value, and then your function decreases from there. So as you go down the tree, your function decreases infinitely often decreases from there. And now, if you just look at my proof, the one that I was talking about on the previous slide, if you just go through that proof was showing that theorem B implied the original tree anti-chain theorem over B sigma 2, right? Now, if you just do that same proof, what that proof is actually showing is that over RCA naught, if you don't assume the additional induction, that theorem B actually implies this weak tree anti-chain theorem. And so this is what I know over RCA naught. All right. Now, the other thing I will sort of point out is that all three of these theorems, the tree anti-chain theorem, theorem B, and the weak tree anti-chain theorem, they're all equivalent over RCA naught plus B sigma 2. So they all become the same thing if you assume B sigma 2. But if you don't assume B sigma 2, I really don't know. I really don't know in terms of the first order consequences of these things, why they are, where they are, or which ones are equivalent or not. And I recall reading some theorems about these first order principles where they have these sort of create these sort of towers of principles, and so that's why I parametrized it by the number n, because I remember reading some papers about these first order properties where it's like well orderings of ordinals and things where you have these towers of principles even below B sigma 2 or I sigma 2 or something like that. And so I parametrized it in this way because they could all be different. I don't know. All right, but they are all equivalent, and the theorem A is in there too. Theorem A is a little bit trickier. Theorem A is also equivalent to the tree anti-chain theorem and the weak tree anti-chain theorem over RCA naught plus B sigma 2. The one thing I will say about theorem A is the proof is a little trickier for theorem A. The proofs are a little bit more non-uniform for theorem A. And so it's one of these situations where you try a strategy, and then if your strategy fails, you end up getting an anti-chain some other way, and you can use the anti-chain to do something. There's just a So you try a certain strategy, and then if that strategy fails, there is a computable anti-chain, within your tree for various reasons. So there is a non-uniform. There's a sort of an extra non-uniformity when you're dealing with theorem A. And so the last point here is just a question. I really have no idea what's going on here in terms of the first order parts. But these are all, I will say, these are all very natural. These are all somewhat natural in terms of the algebra. The algebra leads very naturally to these different tree anti-chain variations, right? And the last thing maybe I should point out here is that the value of the function is actually corresponds to the exponents of the, so on the previous slide, I was talking about it being a principal ideal ring and every ideal is generated by a monomial. The values of the functions here are the exponents of your monomial, of the indeterminants in your monomial. That is where the value of these functions comes from in terms of the algebra. All right. So now I want to say a little bit. I do have some more content here, but I don't, it's this is another talk at this point. But I do want to mention some further results in terms of the primary decomposition lemma, which I haven't really said that much about. So I started off by talking about the primary decomposition lemma in its full generality. And then I talked a little bit about the tree anti-chain theorem. And then I introduced theorem A and theorem B. And since then, I've basically just been talking about theorem A and theorem B, which are weaker versions of the primary decomposition lemma. So let me just say a few things about the primary decomposition lemma. I don't have the results sort of fully written up, but they're, but the results here are actually easier in some ways because I don't have as much, I don't have as much detail to add for the full primary decomposition lemma, but it is interesting. Okay, so before we get to the primary decomposition lemma, I want to remind us of theorem. Like I said, everything I'm talking about, this is all the first 50 to 100 pages of a commutative algebra textbook. And so here's a theorem, another theorem from the first 50 to 100 pages of a commutative algebra textbook. It's called the Krull intersection theorem. And it says that in an integral domain, if you have an ideal and you start intersecting the powers of the ideal, you just end up with zero here, right? And zero here means the zero ideal. That's the Krull intersection theorem. And so one of the, the key hypothesis of the Krull intersection theorem is that you need to be working in an integral domain. And recently I've been looking at this thing in the context of a different project. I've been looking at consequences of the Hilbert basis theorem and analyzing reverse mathematics of some of those principles there. And so in this sort of different project, I was able to show that the Krull intersection theorem implies weak Koenig's lemma. So the Krull intersection theorem implies weak Koenig's lemma. So that's like an aside for now, but I'm going to bring it up again on this slide here. So that's something to keep in mind, that the Krull intersection theorem implies weak Koenig's lemma. But now I want to, after that sort of aside, I want to talk a little bit more about the primary decomposition lemma. So I want to come back to it. So in order to analyze the primary decomposition lemma, we're going to need infinite combinatorial structures that are more general than trees. And so the reason why I could use the tree anti-chain theorem in the previous context, right? The reason why I was talking about trees all through all these slides, the reason why trees worked out in these previous slides is because of this coprime condition back here. It's because I was sort of assuming coprime ideals, and coprime ideals sort of lead to these sorts of splittings. So earlier I was talking about these splittings, x equals y times z. YZ is a sort of a splitting of x. And so remember that x is basically the parent node of the tree, and then y and z become the children. But then I have this other condition here that say a linear combination of y and z is the identity element. And what this basically, what this linear combination requirement basically amounts to is that once you split x into y and z, those two, in some sense, those two ideals, or at least your finite approximations to those two ideals are not contained in a third ideal. And so in some sense, because we have this coprime condition here, once you split, you sort of split forever in terms of the algebra. But in general, if you don't have this coprime condition, you don't know that once you split in this way, you sort of split forever. There could be a third ideal that comes along and sort of contains everything you've seen so far in the first two. And so trees are not going to cut it exactly. Or, I haven't found a way to make trees work out for ideals that are not coprime, And so these coprime conditions, they basically let me use trees in all of these proofs. And those trees are good for modeling coprime ideals. But if you start to talk about ideals that are not necessarily coprime, then I have less to say about that. And you're going to need sort of infinitary combinatorial structures, something like graphs or partial ordering, infinite partial ordering, that are more general than trees, but include something like undirected cycles. And so you could have your tree kind of split for a while, and then you could have like a tree growing at first, and then you could have a node that appears that is simultaneously bigger than more than one leaf in your tree or something like that. You could have these cycles, these sort of undirected cycles appear. And so, I am a little bit less sure about the precise reverse mathematical strength of the primary decomposition lemma. But one thing I can say, and this proof is actually, it's somewhat easier than some of the proofs that I've already talked about, but it's not too hard to show that the primary decomposition lemma follows from the chain anti-chain property. So every infinite partial order has either an infinite chain or an infinite anti-chain, plus WKL naught. And so using these two things, using the chain anti-chain property and WKL naught, you can prove the primary decomposition lemma from the join of those two things. All right, and so for thinking about the converse of this, trying to get a lower bound on the primary decomposition lemma, one of the lemmas that you need sort of do some of the previous proofs that I've talked about. There's sort of a pre-processing step in some of those proofs, but it's kind of interesting that RCA naught can actually prove that if you have a Noetherian ring, then the nil radical of that ring exists, and there's a uniform exponent that kills everything in the nil radical. And so remember that the nil radical is just the set of all nilpotent elements in your ring, right? And you could have elements of your ring that are nilpotent with larger and larger exponents. However, RCA naught says that if your ring is Noetherian and you have these larger and larger exponents, then, well, you can't have the larger and larger exponents if your ring is Noetherian, because if you have these larger and larger exponents, RCA naught, or using annihilator ideals, like a lot of this stuff comes back to just annihilator ideals. Using the right annihilator ideals, you can construct an infinite strictly ascending chain. So it's kind of interesting that RCA naught proves this. This is something that you typically don't find it stated explicitly like this in algebra textbooks typically, because they're not working over RCA naught. So this isn't really that big of a deal for them. But it is interesting. All right. So using this sort of the first bullet point of this lemma here, this is actually a key ingredient in showing that the primary decomposition lemma, it actually implies the Krull intersection theorem that I was talking about earlier. And remember earlier, I also said that the Krull intersection theorem is actually, it implies WKL naught. And so the primary decomposition lemma, it implies WKL naught. And by our previous results, we know that the primary decomposition lemma, because it's stronger than theorems A and B, it also implies the tree anti-chain theorem. And so we know that the primary decomposition lemma actually implies, it implies a Krull intersection theorem, so it implies WKL naught, and it implies the tree anti-chain theorem as well, and so it implies the join of the tree anti-chain theorem and WKL naught. And so we know that it's somewhere in between the chain anti-chain theorem and WKL naught and the tree anti-chain theorem and WKL naught. And so in particular, it's going to fall outside of the big five subsystems of second order arithmetic, and it's going to fall somewhere, sort of strictly in between ACA naught and WKL naught. And the last thing I will say, just the very last thing I will say, is that the proof that the primary decomposition lemma implies the Krull intersection theorem. This is not something that you typically find actually in standard algebra textbooks. You sort of need to go to something like a professor's lecture notes to find something like this. This is something that you won't see in standard text, but it's something that I first discovered just doing a search on Stack Overflow, following a few links from there. Doing a lot of this reverse math stuff, you need to find if it's interesting enough, you need to find like idiosyncratic sources that actually give you the strength of these things, that point you in the right direction. And so something like a professor's lecture notes, if your theorem is sort of interesting enough, you need something like professor's lecture notes sometimes to really get at it. Anyway, so that's all that I have to say for now.
Okay, let's thank Chris. Thank you, Chris. Nice talk. We'll open it up for questions. Anybody have questions?
Yes, I thank you very much for the talk, and I wondered if you have looked at the computable content of say, the second formulation of the tree anti-chain theorem of the TAC. I mean, from what you said, I gathered that any computable instance would have a solution computable from 0 double prime. But can you say more than that? Would it have a delta 2 solution or a low 2 solution or a pi 2 solution or anything of that nature?
Yeah, so it has a delta. So it has a delta 2 solution.
Oh, okay.
It has a delta 2 solution. Yeah.
Thank you.
Other questions? You have to speak up and just unmute yourself and talk.
Chris, I have a quick question about the B sigma 2. So is it consistent with what you know that TAC might imply B sigma 2?
Yeah, because I don't really know much. Yeah. I don't think it does, to tell you the truth, but it might. Oh, I see, because of the 2 random thing.
Well, actually, no, I'm looking at the chart in the Hirschfeld-Shore paper, and there it says that both TAC and ADS imply B sigma 2. Well, modulo a small theorem, that part is the same as B sigma 2. So I'm just wondering whether TAC is another principle that might just straight out imply B sigma 2.
It might. Yeah. I don't have a good feel for it. I don't think it. I especially don't think the weak one does. WTAC. That's the one that I really don't think does. But I do think that those are different. But I don't know. My opinion's not worth that much for these first order things, even for the second order. But depending on how much I've thought about it, but you know, it's
anyway, something worth thinking about.
Yeah, definitely. I think it's interesting. I wanted to say more the other week. Jeff Hurst asked me this question a couple of weeks ago, and I wanted to say more. I think it's interesting, and you get it from the algebra actually pretty easily. And it's it's like, how do you weaken an anti-chain theorem like that? But it falls out of the algebra pretty naturally. So it's interesting.
Thanks.
Any more questions? You could chat me or just unmute yourself and ask.
Well, I'll try one more on the same theme of the computational content. Does every computable instance of TA2 have a low solution?
That I know less.
Because that would be really interesting. Oh, maybe you could refute that, because that
I don't
build a mega model of WKL naught where TAC holds. I'm sorry, where? Yeah, consisting of low sets where TAC holds. That seems unlikely. Probably that's false.
I would guess that it's unlikely. I guess that it's unlikely. You can, the way that you prove it, it doesn't follow from WKL is you diagonalize against these HCE, right? Or for these different order functions. So for any order function H, right, you can prove that there's a tree so that no solution is HCE. I'm not sure if that gives you the low thing. I'm not sure if that.
I don't think so.
Yeah, I can't see any reason why I would, but.
Okay, let's thank Chris again one more time. So I'm going to stop the recording and then